Yeah? 1, 2, 3, 4, 5. Yeah? And interesting for us are obviously the last two entries here, delta, which correspond to delta 3 and delta 4. So once we have defined our new matrix, X matrix, our Y matrix, our Y vector, our X matrix, we know what our beta vector is. We can implement OLS here, given these definitions. Let's take this away. So we know our formula beta hat is X transposed X inverted X transposed Y. So what we get is our parameter vector, beta hat, which has the delta 0 hat, delta 1 hat, delta hat 2, delta hat 3, and delta hat 4. So then we know our error vector for this regression equation, this E hat, is given by Y minus X times this beta hat here from that equation. We know that the variance of that guy here, beta hat, is defined as 1 over this guy here transposed, epsilon transposed times itself, from that equation, times X transposed X inverted. So what we know is that what comes out here is a covariance matrix that has the dimension 5 by 5. Okay, this is a 5 by 1 vector. So our covariance matrix has the corresponding dimension 5 by 5. We know the first element on the main diagonal is the variance of this guy here, or delta 0. Second element on the main diagonal is the variance of delta 1, and so on. And we are interested in the fourth and the fifth element on the main diagonal of that matrix here. So we estimate the t-statistic for our delta hat 3 and delta hat 4, very simple, like we usually do. We take the point estimator, delta hat 3, and divide it by the square root of that element here, of the fourth element on the main diagonal of our estimated covariance matrix. So that's the t-statistic. That's the t-statistic for our delta hat 3. In the same manner, we estimate the t-statistic for our delta hat 4 by taking our delta hat 4 and dividing it by the last element here on the main diagonal of the covariance matrix and take the square root. Let's take this away. So again, we have to check the t-statistics of our delta 3 and our delta 4. So whenever our t-statistic indicate that it's the value is higher than 1.96, obviously then on a 5% significance level, we would argue that the volatility of the asset 2 has an impact on, or has a significant impact on the volatility of asset 1. And the same is, of course, if the delta 4 has a t-statistic that is larger than 1.96. Yeah. So it's enough if one of these parameters has obviously a t-statistic that is larger than 1.96. Yeah. So in either case, we would argue that the asset 2 has a significant impact on the volatility of asset 1. And of course, we can also change the lag order, and the implementation of higher lag orders is straightforward. And again, of course, we can expand this equation for the conditional variance. Yeah, we can put in any variable and test with a t-statistic if the variable has an impact on the volatility process of a specific asset. Yeah? So the procedure is always the same. Yeah? So you have an equation for the mean, you have an equation for the conditional volatility. Yeah? So we square this guy. First we estimate the regression residuals for the mean equation, and also the mean equation can be different. Either you have just an intercept term, or you have past lags of the asset itself, yeah, what some people do, who knows why, or you have any other regressors here, like a factor model, for instance. Yeah? And what you get is a residual here, an estimated residual, yeah? And you square them, yeah? And you regress this squared residuals from the mean equation on past or on lagged squared residuals, which have a certain autocorrelation order here, capital P. Yeah, it can be 1. It's the simplest case. Then you have an arch1 model, obviously, or it can be 5 or whatever. If you want to test then if other variables, like for instance the volatility or past squared residuals, yeah, of other assets, have an impact on the volatility, on the conditional volatility process of our specific asset here, you just add them here in the equation for the conditional variance, or for the conditional variance, because you square it, obviously, if you run the regression. So, and whenever the point estimator here in that equation are significant, then obviously you would conclude that they have a significant impact on that asset's conditional volatility. Yeah? So after we discuss the volatility process, what we will do next is we will discuss a very important econometric test that is often used, or that is very simple to implement, and this test is called the so-called LM test. We already encountered a very special version of the test in our when we implemented the test for arch effects, which is often referred to as the arch LM test. But that's obviously a test for that is related to the second moment, where we basically square of the residuals here. But the standard LM test works slightly different, and this is what we would like to discuss next.